Okay, looks like we are now done with lexical analysis specifically, and we're moving on to syntactic analysis and parsing. So yeah, let's get started. We're going to do lesson 4, grammars and parsing. Context-free grammars. We have now completed lexical analysis. Oh, uh, one other thing, I didn't really do any Anki's for the conversion of NFAs to DFAs, conversion of regular expressions to DFAs and NFAs and all that stuff because I'm worried that that's going a bit too deep for what I want to get out of this course. Really, I wanted to get out the higher level idea of how to build compilers, not specifically, how to convert NFAs to DFAs and whatnot. If I do need that in the future, I can always just look that up. And now that I've done it once, it's going to be a lot easier to remember it in the future. So that's why I didn't do that. Actually, now that I think about it, before we get into this, we should probably do some Anki. Probably like study Anki itself. So let's do that real quick. Okay. What does an assembler do? An assembler takes assembly code from the compiler and it creates relocatable machine code. Good. What does semantics mean? In this context, it means the correctness of a language according to some specific definition of a language. Good. What is semantic analysis? It's the third step in compiling where you take an abstract syntax tree and you do type checking on it and you check for semantic correctness. Make sure it's a valid program, essentially. Yep, good. What is syntactic analysis? This is what we're going to be studying today. It's the second step in compiling. It's where you take a stream of tokens from the lexical analysis phase and you convert that into an abstract syntax tree that, literally represents the syntax of the language. Good. Lexical analysis. Study now. What does this match? This matches A concatenated with the empty string, which is the set containing A. Good. What does this match? This matches A or B or C. Pretty much. Yep. What does this match? Question mark. That essentially matches R, or the language of R, or the empty string. Yep, so R union with the empty string. Good. What is a lexa generator? A lexa generator is a program. For example, the Flex program on Unix, which takes a regular expression. It takes a language specification, which you specify using regular expressions, and it converts that into I think it's a C program, or in this case, it's a C program that does the lexing for you, essentially. Yep, pretty good. What is this called? That's the clean closure of L. That represents 0 or more instances of L. What does this match? This matches any character except A or B or C. Good. What is this called? That's the the positive closure of L, which matches one or more instances of L concatenated together. Good. What does this match? Dot matches. Oh, I think that matches any character except new line character. Yes. Sweet. All right. Let's get into what are we doing? Syntactic analysis. We've now completed lexical analysis. Our input program has been converted into a stream of tokens. The next step is syntactic analysis, or parsing, in which the compiler will read the token stream and recognize whether the tokens represent valid language syntax. Typically, the parser will also construct a tree representation of the program for use by later compiler phases. The parser does not in general complete the task of recognizing whether the program is legal. For example, a compiler will often check that types of expressions agree appropriately and that variables are declared. A compiler will often check that types of expressions agree and that variables are declared. These static checks are usually the job of the next compiler phase, semantic analysis. Parsing is a well-established part of computer science, but it is worth understanding how to do well because many programs, not just compilers, need to parse information. Alright, context-free grammars. We take the approach in this course of building implementations from precise specifications. How might we specify legal syntax of programs in a programming language? We saw that for a problem of specifying legal tokens, regular expressions give us sufficiently expressive we saw that for a problem of specifying legal tokens, regular expressions give us sufficiently expressive specification language. Unfortunately, regular expressions are not expressive enough for most programming languages. An easy way to see this is by considering the need to check whether parentheses and other grouping constructs are properly balanced. Yeah, in order to balance parentheses, it is necessary to count the number of open parentheses that have not yet been closed. Yeah, so you could have tons of these. However, regular expressions can be recognized by finite automata, whereas to count an unbounded number of parentheses would require an unbounded number of states. No finite automaton can keep track of the number of unbalanced parentheses, so regular expressions are not powerful enough to specify the language syntax. This limitation of regular expressions motivates the use of context-free grammars. We looked at that in, I think, probably the second video of this series, I think it was, very briefly. So we're going to dive into that here. A context-free grammar is characterized by a set of productions. Okay. Each production explains how to rewrite a non-terminal symbol into some sequence of terminal symbols, tokens, or non-terminal symbols. For example, we can define a language of arithmetic expressions, including balanced parentheses, using a context-free grammar with non-terminals S and E. Okay, so S plus S, I'm not sure what I'm reading here. As an abbreviation, we typically borrow regex notation and write all the right-hand sides for a given non-terminal together. Still not sure what a non-terminal symbol or a terminal symbol is. So S becomes S plus S. So S can be S plus S or S times S or E, or this non-terminal E. E can be N or S in parentheses. The non-terminal S is the start symbol for the grammar. The symbols plus, asterisk, N, and these parentheses are terminals. tokens. Here the token n represents some literal number. Okay, I'm gonna have to dive a bit deeper on that. What is a set of productions? Let's look that up. Let's ask ChatGPT about that. In the context of context-free grammars, what are productions? Terminal symbols and non-terminal symbols. Several key elements play central roles in defining the grammar and generating valid strings. These elements include productions, terminal symbols, and non-terminal symbols. Productions, or rules. Productions are the fundamental building blocks of a context-free grammar. They define the rules for generating valid strings in the language. Each production consists of a non-terminal symbol, the left-hand side, and a sequence of symbols comprising non-terminal and/or terminal symbols called the right-hand side. Okay. So the non-terminal symbol is the left-hand side, makes things easier. A production can be written as A goes to B, where A is a non-terminal symbol and beta is a sequence of symbols, which can include non-terminals and terminals. So what's a terminal then? Productions describe how non-terminals can be replaced by other symbols, including non-terminals and terminals. Okay, so they're like a formula, essentially. Terminal symbols. Terminal symbols are the symbols in the alphabet of the language generated by the context-free grammar. The symbols in the alphabet of the language generated by the context-free grammar. They are the symbols that appear in the valid strings of the language. Okay. Terminal symbols cannot be further expanded or replaced within the grammar. Terminal symbols cannot be further expanded or replaced within the grammar. Okay, so they're like, so they're like the more base values. In a production rule, the right-hand side may contain a mix of non-terminals and terminals. Makes sense? Terminal symbols are often characters, keywords, or tokens in a programming language, such as letters, digits, operators. Okay. Terminals are tokens. Non-terminal symbols, what are they? Placeholders or variables that can be replaced by sequences of symbols according to the production rules. Non-terminals represent categories or syntactic constructs in the language. Non-terminals are used to define the structure and syntax of the language. They provide a way to create hierarchical structures within the grammar, allowing for the definition of complex language rules. Non-terminals do not appear directly in the valid strings, but are involved in the process of generating them. Productions define how non-terminals can be expanded into sequences of non-terminals and terminals. By applying these productions recursively, you can generate valid strings in the language. Makes sense? The terminal symbols are the symbols that appear in the final strings, while the non-terminals help define the structure and syntax of the language. Alright, so I'm definitely going to need to remember these. Probably going to forget this really easily, so let's make a new deck for grammars. What was this lesson called? I think it was like grammars and parsing or something. Fix that later. Alright, so what is a reduction? So a reduction is its fundamental building block of the context-free grammar. They define the rules for generating valid strings. Just a little note to myself. Don't expect myself to remember this every time. They contain the terminal and non-terminal symbols. Just a little bit more context whenever I read this ticket. Context, free grammars. What are terminal symbols? So they're essentially the symbols in the alphabet. So they're the valid strings, they're the valid like matches to the regex, they're the valid tokens. It cannot be further expanded or replaced within the grammar. So how do we put this? They are the symbols. Valid strings. The symbols that appear in the valid strings of the language, they can't be broken down further, nor can they be replaced within the grammar. Or they can't be expanded. They can't be expanded or replaced within the grammar. And finally, what are non-terminal symbols? They're placeholders for variables that can basically contain terminal symbols and other non-terminal symbols. Right, so if it's terminal, so you just got to remember if it's terminal, it can't be expanded or replaced. If it's non-terminal, it can be a substitute, like it can represent a sequence of non-terminal symbols or even more, terminal symbols or even more non-terminal symbols. So they're the variables on the left-hand side of the grammars generally. Bit of context. Okay. We can define a language of arithmetic expressions, including balanced parentheses, using a context-free grammar with non-terminals S and E. So we've got our non-terminals S and E, which includes, so this would be, oh, okay, right. So this shows, I'm guessing this represents the associative property of addition, because you can substitute S in here and it could expand out to being like S can equal S plus S, but then each of these S's can expand to be S plus S plus S plus S plus S plus S, and so on. Cool. S can equal the non-terminal E. E is a literal. I think that was saying that represents a literal. Here the token N represents some literal number. Cool. E can be some non-terminal inside parentheses. So these are terminals. I'm guessing N is a terminal as well in this instance. Yep, N are terminals. Right, so yeah. So the open and closed parentheses represent terminals, and the S can be anything, basically. Derivations. Given a grammar G, a string in its language, language of G, if there exists some derivation of the string using G. Sorry, a string is in its language, language of G, if there exists some derivation of the string using G. A derivation is a sequence of rewrites that starts with the start symbol and eventually rewrites it into the string. A derivation is a sequence of rewrites that starts with the start symbol and eventually rewrites it into the string. Okay? Each step in the sequence applies some production of the grammar. Okay? It does a rewrite alpha A beta to alpha, I don't know what that symbol is. Something, is it just a Y? Y beta, where A to Y is a production. Okay, alright. The grammar is called context-free because whether the production applies doesn't depend on the surrounding context A and B. That makes sense in this specific world. For example, the string 1 plus 4 plus 2 is in the language of the grammar. We can see this by constructing a derivation. S goes to S plus S. It's the same as E plus S. Is the same as S within brackets plus S. Is the same as S plus S inside brackets plus S. It's the same as E plus S inside brackets plus S, etc. 1 plus E. Wait a minute. You've lost me. Okay, so yeah, okay, so S can equal E and E can equal some literal. So this is totally valid for S to equal 1. S can equal any literals. So S can equal 4. Yeah, so I guess they're just subbing in. They're subbing in E for S, and then literals for E. And eventually we arrive at 1 plus 4 plus 2. This derivation is a leftmost derivation. At each step, the non-terminal that is expanded is the leftmost non-terminal in the string. As we see soon, leftmost derivations are constructed by top-down parsers. It is also possible to construct a rightmost derivation for any string, expanding the rightmost non-terminal at each step. For example, the rightmost derivation of the same string proceeds as follows. So we start at s, which is s plus s, and we know that s can go to e. We do this on the right hand, we do this on the far right hand side, and then we know that e can be some literal, and then we just turn it into a literal. So the next step is we know that s can equal e, and we know that e can equal in s surrounded by parentheses. So we sub that in, plus 2, then we expand that to s plus s, then we know that s can equal e, and we know that e can equal some literal, and then finally we finish the last one off. Cool. It's also possible to construct a rightmost derivation for any string, expanding on the rightmost non-terminal. So we did it leftwise here, right? So we converted s to e, then into some parentheses surrounding s, which turns into s plus s, then it turns into e and turns into a literal, then turns the next one into a literal, and so on. Actually, now that I think about that, C++, what was this project? I saw a project that was talking about something like this. JSON. Yeah, I think this is it. Contributing. Is it FAQ? Basically, I think it was these guys. They were talking about they wanted contributors for their project, and they wanted someone to do a parser that was like rightmost. Oh, I'm probably misremembering this, but it'd be really cool if we could learn how to build the the parser the parser type that they actually want, and then contribute to this project. I might make that a video series in the future if this is what we're actually learning here. That would be really cool. I'll have to look more into this. Oh, where was it? I know it was this. I know it was this. It wasn't the README. Was there a contributing document? Here you go. Contribution guidelines. Here we go. Yeah, so wanted. Improving the efficiency of the JSON parser. The current parser is implemented as a naive recursive descent parser with hand-coded string handling. More sophisticated approaches like LALR parsers would really be appreciated. LALR. That said, parser generators like Bison or Antler do not play nice with single header files. I really would like to keep the parser inside the JSON. Yep. I am not aware of approaches similar to RE2C for parsing. So, what is an LALR parser? Asking ChatGPT. Look ahead, left to right, rightmost. Parser is a tough parser used in computer science. Analyze the syntax of programming language is variant of the left to rightmost parser. So the LR parser. So is that what we just... okay, so we have... This derivation is the leftmost derivation, constructed by top-down parsers. LALR parsers use a bottom-up parsing algorithm, which means they start from the input tokens and build the parse tree by repeatedly applying reduction. Look ahead means that the parser examines one or more tokens ahead to decide whether to shift or reduce. This look ahead allows LALR parsers to handle a broader class of grammars than simple LR parsers. More memory efficient and faster. They have smaller parsing tables, making them practical for real-world programming languages with complex grammars. They're table-driven, error handling, etc. Okay, so it would be actually super cool if this series, this course could teach us how to implement an LALR parser. And if it does, like, I'm so gonna attempt to contribute to this. Even if I fail miserably, I put up a pull request and these guys just laugh at me. I don't care. I just think it would be super cool to attempt something like that. Alright, so as we see soon, leftmost derivations are constructed by top-down parsers. It's also possible to construct a rightmost derivation for any string, expanding the rightmost non-terminal at each step. So this is a top-down parser. So what is a top-down parser? Top-down parsing is a parsing strategy where one first looks at the higher level of the parse tree, works down the parse tree by using the rewriting rules of formal grammar. LL parsers are a type of parser that uses a top-down parsing strategy. Top-down parsing is a strategy of analyzing unknown data relationships by hypothesizing general parse tree structures and then considering whether the known fundamental structures are compatible with the hypothesis. It occurs in the analysis of both natural languages and computer languages. Top-down parsing can be viewed as an attempt to find the leftmost derivations of an input stream by searching for parse trees using a top-down expansion of the given formal grammar rules. Inclusive choice is used to accommodate ambiguity by expanding all alternative right-hand sides of grammar rules. Still not clear on what the difference is. I'm going to ask ChatGPT for this. What is... the bottom up, right? Top down and bottom up parsers are two distinct approaches. So top down. The parser starts from the root of the parse tree and works its way down to the leaves. Begins with the start symbol of the grammar and attempts to find a sequence of productions that match the input string. Top-down parsers start at the highest level of abstraction and recursively expand non-terminals till they match the input string. Okay, right, okay, so we start at the highest level, we expand the non-terminal out, and then we keep expanding that out and attempt to match the string eventually. Is often implemented using recursive descent parsing or LL parsing. Okay, so this is what these guys in this, let's close that for now. This is what these guys are doing. The current parser is implemented as a naive recursive descent parser with hand-coded string handling. Recursive descent parsing is a manual handwritten approach where each non-terminal has a corresponding function that attempts to match the input. Okay. LL parsing is table-driven and efficient, used for predictive parsing. Top-down parser is commonly used when the grammar is LL1. Don't know what that means. Hopefully we will learn that in the future. I'll come back to this. Ambiguity. Top-down parsers may struggle with ambiguous grammars that allow multiple interpretations of the same input, and grammar transformations may be necessary to make them unambiguous. Okay. Bottom-up parsing. In bottom-up parsing, the parser starts with the input string, and works its way up to the root of the parse tree. It begins with the input symbols and applies productions in reverse, attempting to build the parse tree. Oh, okay. Right. That makes sense now. So instead of starting at the highest level of abstraction, we start down here with our actual string, then we attempt to match non-terminals that encompass the terminals, essentially. So here we find E, which can represent a literal, an integer literal, and then we keep doing that. So these guys want one that is LALR. What is LA? Look ahead, left to right, rightmost. So I'm guessing we just start left, work our way right over the string. Cool. That makes sense. I'm gonna bookmark this so that I can look this up in the future for sure. Let me do that now. Bookmark, current tab. Done. Cool. Alright, continue on. Parse trees and ambiguity. A derivation corresponds to a parse tree in which the root is the start symbol and the leaves are the final string. Okay, makes sense? Both of the derivations above correspond to the following parse tree. So S can be expanded to S plus S, and S is equivalent to E, and E is equivalent to S inside these parentheses, and we know that S is equivalent to S plus S, or can be equivalent to S plus S, and then we know that S can be replaced with E, and E can be replaced with any literal. Okay, I see how this is like building the syntax. This is really cool. Although these two derivations both generate the same parse tree, it is also possible in general that a string can have more than one parse tree. When that happens, the grammar is said to be ambiguous. I want to see an example, but I guess if S can equal S plus S, but also it can equal S times S, Yeah, I don't know. I guess that's what they're getting at. It is also possible in general the string. An ambiguous grammar is one for which there is some string with multiple parse trees. Our example grammar is in fact ambiguous. For example, consider the string 2 plus 3 plus 4. Yeah. It has one parse tree in which the production s is equivalent to s plus s is used at the root, but another parse in which the production s is equivalent to s times s is used at the root. Considered as arithmetic expressions, the first parse tree corresponds to the expected value of the expression, 14. The second parse tree corresponds to computing 20, arguably the wrong answer. The problem with the grammar is that it does not enforce precedence or associativity of the operators plus and multiply. Is that what I want to know? Is that issue part of semantics, or is it handled syntactically here? I guess we're about to find out. Enforcing precedence and associativity. Enforcing precedence and associativity is a common problem when designing a grammar. Fortunately, there are some standard ways to do it. The problem with the original grammar is that it allows the production s to s plus s to appear in the parse tree directly under the production s to s times s. We can prevent such parse trees by introducing separate non-terminals to represent different precedent levels. Okay, fair enough. For example, we can say that an arithmetic expression is a sum of one or more terms, t, where each term is a product of one or more factors, f. Okay, so s can be expanded to s plus some term or some other term. Wait. There's a sum of one or more terms t, where each term is a product of one or more factors f. So a term can be defined as t times some factor. I'm not sure what this means. T or t, f or f. Can it mean s plus t or t? T is equivalent to t times f or f, as in like parentheses around the t and f. That could be it. And f is equivalent to some literal or s inside brackets. This grammar prevents a sum from appearing under a product unless it is surrounded by parentheses. This grammar prevents a sum from appearing under a product. Yeah. This grammar also enforces left associativity of the operators plus and asterisk. This restriction arises because the production s is equivalent to s plus t is left recursive. The symbol s appears in the productions only as the first symbol. Conversely, if we want a binary operator to be right associative, we would use a right recursive production like s. Conversely, if we want a binary operator to be right associative, we would use a right recursive production like s to. I don't quite understand the significance of left recursive and right recursive in the context of arithmetic, like associativity and precedence. Probably gonna have to pose this to ChatGPT, get it to dumb it down for me. Some parser generators, such as CUP, Yak, and Bison, allow precedence and associativity ambiguities to be resolved through precedence declarations. For example, in CUP, the following declarations make plus and times left associative and make times higher precedence than plus. Okay, so just defining precedence left plus, precedence left times, I guess whichever one's the last defined takes the highest precedent. Precedence declarations prevent parsers that violate the precedence and associativity constraints. We see later how this works in more detail. Alright, I'm going to end this session and we'll pick up the video next time. Alright, back into it. So I just got to reread this to refresh my memory. Enforcing precedence and associativity is a common problem when designing a grammar. Fortunately, there are some standard ways to do it. The problem with the original grammar is it allows the production S is equivalent to S plus S to appear in the parse tree directly under the production S times S. We prevent such parse trees by introducing separate non-terminals to represent different precedence levels. So for example, we can say that an arithmetic expression is a sum of one or more terms t, where each term is a product of one or more factors f. An arithmetic expression is the sum of one or more terms t, so S can be an arithmetic expression which is the sum of, which can equal t, or it can equal, so in the base case it would equal t, and then in the recursive case it would be itself plus t, where each term is a product of one or more factors f. So t itself can be equal to, in the base case, some factor, or it can be equal to itself times some factor. Alright, that makes sense. And then f can be equal to some literal, or a sum surrounded by parentheses. This grammar prevents a sum from appearing under a product unless it is surrounded by parentheses. This grammar also enforces the left associativity of the operators plus an asterisk. This restriction arises because the production S is equivalent to S plus T is left recursive. The symbol S appears in the productions only as the first symbol. Conversely, if we want a binary operator to be right associative, we would use a right recursive production, like S is equivalent to T plus S. Some parser generators such as CUP, can bias and allow precedence and associativity ambiguities to be resolved through precedence declarations, which is a lot easier to understand. For example, in CUP, the following declarations make plus and times left associative and make times higher precedence than plus. Precedence declarations prevent parsers that violate the precedence and associativity constraints. We see later how this works in more detail. Alright, so I'm just going to add something to Anki for this, because this is something that enforcing precedence is important, and I'm probably going to forget this. So how do you enforce precedence for arithmetic for productions that include arithmetic. The answer is, you can do it two ways, I guess. You can prevent such parse trees by introducing separate non-terminals to represent different precedence levels. Use separate non-terminals. Different precedence levels. So that makes sense. You're essentially forcing a plus operator to appear before a multiplication operator, unless the plus operator is surrounded by parentheses. Wonder if this will copy straight in. I'm not expecting myself to remember this whole thing. This is just for context. Basically show you how to force precedence. The above context-free grammar forces appears in so the gist of it is expand your non-terminals out, use separate non-terminals to force precedence this way. And then you can have a case where parentheses negates that. Cool. The dangling else problem. Most programming languages have an if-then-else construct, which naturally leads to ambiguity. Consider the following simplified grammar for statements. S, if E, then S is equivalent to if E, then S. Or if E, then S, else S. Or some other value. If we use this grammar to parse a string of the form if E1, then if E2, then S1, else S2, there are two possible parsers. One in which the else clause attaches to the first if, and one in which it attaches to the second. If E1, then if E2, then S1, else S2. Most languages implement the closest if rule. An else attaches to the closest preceding if. To solve this problem, we observe that there are two kinds of statements. unmatched statements that end in a string of the form then S, and matched statements such as if E then S1 else S2 that do not. String of the form then S, and matched statements such as if E then S1 else S2. The insight is that we cannot allow an unmatched statement to be followed by an else. Okay, because then the closest if rule would require the else clause to be part of the unmatched if. So unmatched if statements end in a string of the form then S. Match statements such as else, so an if has an else. The insight is that we cannot allow an unmatched statement to be followed by an else, because then the closest if rule would require the else clause to be part of the unmatched if. This intuition can be captured by introducing separate non-terminals to represent matched and unmatched. So, a matched non-terminal is if E then M else M, some other. If unmatched is if E then S, if E then if E then M else U. The key is that both productions that include else require that the preceding statement be a match statement. In CUP and similar parser generators, it turns out the dangling else problem can also be solved through precedence declarations. Precedence non-associated if else. To solve this problem means that there are two kinds of if statements. Sorry, there are two kinds of statements. Unmatched statements that end in a string of the form then S, so like that, and matched statements such as if E then S1 then else S2 that do not. So that's matched. Insight is that we cannot allow an unmatched statement to be followed by an else. Because then the closest if rule would require the else clause to be part of the unmatched if. This intuition can be captured by introducing separate non-terminals. Let's try and draw this out. Try and understand what they're saying here. So, if we have M is a match statement, so if we have if E then something else something, and M can be basically itself so it can be itself and then like other. So a match statement can be something like that. It's not far enough. Makes sense? So U is looks like if E then M else itself. So it can look like if E then M. If E then S. Else U, which could be something like that. Right, so those two things, so those two are legal, whereas this one is broken. This one would be if E then something then L then S, or it could be if E then S else S. If E then S then S. Not 100% clear on this. Parsing. Dangling else is a problem in programming a parser generates which an optional else clause in an if then else statement results in nested conditionals. Being ambiguous. Following the reference context-free grammar. Language is ambiguous, meaning there is more than one correct parse tree. In many programming languages, one may write conditionally execute code in two forms: the if-then form, the if-then-else form. The else clause is optional. If A, then S. If B, then S1, else S2. This gives rise to an ambiguity in interpretation when there are nested statements. Especially whenever an if-then form appears as S1. Right, so if we replace this with an if-then, right, okay, so, right. Let's see what they're saying. Let's see what they're saying now. So, yeah, that makes sense. So, pretty much, when you sub in, let's go red, that statement by itself is perfectly valid. However, in the context of the entire thing, the else wants to close this if. So it wants to close this if because it's the closest if. However, it should be closing this if. That makes sense. Because, well, yeah, when you parse that, you can't see the... You can't necessarily see that this is supposed to be nested. It's just sort of reading it one token at a time. Okay, so to fix this, we observe there are two kinds of statements. Unmatched statements at the end of a string of the form then S. Yep, so this would be an unmatched statement in here. And matched statements. The insight is that we cannot allow an unmatched statement to be followed by an else, because then the closest if rule would require the else clause. Yep. So okay, so we can't allow this to be followed by an else. Intuition can be captured by introducing separate non-terminals that represent matched and unmatched. So a matched statement is this, or some other, or some other. An unmatched is this, or this else followed by another unmatched statement. The key is that both productions that include else require that the preceding statement be a matched statement. The key is that both productions that include else require that the preceding statement be a matched statement. So the unmatched statement can be of the form if E then S, that's fine. And that's kind of like its base case. And then it can also be of the form if E then some matched statement else another unmatched statement. Right, so we have to force... I still don't understand how we would force that. So what we're seeing here is... Let's get rid of this stuff. So so that's unmatched, whereas the outer one is... The outer one should be matched. Both production does require that the preceding statement be a match statement. So, okay, so yeah, so if we're going to have an unmatched statement, we have to have, it has to be after a match statement, which is fine, but what if you, this is literally your string, then what? I guess you have to, this somehow represents it properly, so if U equals E, then S, so you have to treat this as one full statement, right? So that way, so you have to treat, yeah, you have to treat that last bit as a full statement, then you go in and parse that statement separately, which is a matched statement. So that counts as a matched statement. So this is, so U encompasses that entire thing, contains S, and then you go in and parse that as a match statement. I think. I hope that's what they're trying to say. All right. Other parsing issues. Some programming languages pose extra challenges for parsing. For example, significant white space has, after a multi-decade hiatus, again become popular in languages like Python, Haskell, and JavaScript. Indentation levels in Python and Haskell implicitly signal the grouping of expressions. The usual strategy for parsing languages with this feature is for the lexer to insert additional tokens at points where the indentation level changes. These are known as indent-dedent tokens. These tokens can then be used in the language grammar as if they were invisible parentheses or braces. This kind of strategy is not needed for the ETA language because these tokens can then be used in language grammar as if they were invisible parentheses or braces. This kind of strategy is not needed for the ETA language because although it makes semicolons optional, it is not whitespace sensitive. Another challenge is languages that distinguish different categories of identifiers. The lexer should generate different token types for different kinds of identifiers. In some languages, like OCaml, this distinction is not a problem because the identifier category can be determined purely lexically. However, languages C and C++ are harder to handle. For example, the correct parse for the statement hash table of type generic type K and V X depends on whether hash table is the name of the class. It depends on whether hash table is the name of a class. If it is the name of an integer variable, then the statement actually describes two comparisons among 4 variables. Yeah, I guess. So you have hash table is less than K and V is greater than X. To generate different kinds of tokens for different kinds of identifiers, information from later stages of the compiler are needed while performing lexical analysis. This lexer feedback makes the compiler more complex and fragile since compilation is no longer a simple linear sequence of transformations. Another technique for dealing with ambiguous parsers is to defer the problem until later compiler phases when more information is available, such as the entire abstract syntax tree for the program. This approach works well when it is not necessary to resolve the This approach works well when it is not necessary to resolve the ambiguity to get the structure of the parse tree mostly right, which is not the case in C++, as the example shows. Recursive descent parsing. Should I write this down? No, it's fairly simple. Recursive descent parsing. What is that? Recursive descent parsers are an example of top-down parsers. Decide how to build the parse tree from the top down as they read in input. Perhaps the most familiar example of a top-down parser is a recursive descent parser, in which the parser is structured as a set of potentially mutually recursive functions. However, top-down parsers can also be structured as table-driven code that uses a stack instead of recursion. Top-down parsers are known as LL parsers, where the first L stands for left to right, and the second L stands for leftmost. An LL parser reads its input left to right and constructs a leftmost derivation as it does so. LL parsers cannot handle all grammars, or even all unambiguous grammars. An example of a grammar they can handle is the following grammar for S expressions. Which were invented by John McCarthy for the programming language Lisp, a precursor of modern functional languages. S is equivalent to X or L in parentheses. L is equivalent to the empty string or S concatenated with L, I'm guessing. So they can handle this grammar for S expressions. An example of an S expression is the expansion let x to x plus 1, which in the programming language scheme, a Lisp descendant, is roughly equivalent to the Oat-Camel expression let x equals 2 in x plus 1. Because of the nice properties of this grammar, we can directly write a recursive function. What does that mean? A simple example of using the let construct to create a local variable x and perform an addition operation. Let x equals 2, this part of the code, simple. The in keyword separates the variable declaration from the expression that follows. It indicates that the variable x is available for use within the expression that follows. This is the expression that uses the variable x. It calculates the value of x plus 1, which is 2 plus 1, resulting in 3. So in summary, this is okay. So why? It's indeed more straightforward to declare the variable as 3. However, the code you provided is a minimal illustration. In real-world code, variable assignments like let x equals 2 in often serve more complex purposes and are useful for a variety of reasons. Dynamic values in actual code, the value assigned to a variable might be computed or retrieved through some dynamic or complex operation. For example, you might read a value from a file, perform a database query. Okay. Code organization, reusability. Environments like the Oat-Camel read-about print loop, you might want to assign values to variables and experiment with different expressions using those variables. It's a way to indirectly explore and manipulate values. Cool. I do want to learn a camel eventually. Alright, so example of an S expression. Because of the nice properties of this grammar, we can directly write a recursive function to recognize an input stream containing an expansion of the non-terminal S. Because of the nice properties, we can directly write a recursive function to recognize an input stream containing expansion of the non-terminal S. Here's pseudocode. Alright, so to parse S, pick the next character if it's an ID. I guess it won't pick the next character. If it's an ID, scan it and return it. If it's a left parentheses, scan the left parentheses, then parse L on whatever's inside, and then we scan the right parentheses and return. Cool. In this code, we rely on a function peek that reports the type of the next token that the lexer is ready to return. Okay. We pick a token, right? Because we're not in lexical analysis. We're not doing lexical analysis anymore. Rely on a function peek that reports the type of the next token that the lexer is ready to return, and another function scan that reads and returns the next token, while also checking that the token is of the expected type. Cool. Given that we are expecting an S on the input, the next token we see immediately allows predicting which S production should be used. Hence, an LL parser is also known as a predictive parser. Given an expected non-terminal and a look-ahead token, it can predict the production to use. So this scan, wait a minute. No, so the peek, yeah, we peek, and if it's the case of an ID or a left parentheses, then we do what we gotta do. Similarly, we can implement a recursive function to recognize an L on the input stream. Parse L. Switch, pick the next token. If it's an ID, looks like we use this grammar S. So L is equivalent to S concatenated with L. If it's a left parentheses, we parse S and then parse L. If it's a right parentheses, L is equal to the empty string, so we return. Okay. In a recursive descent parser, non-terminals in the grammar are implemented as functions. In a recursive descent parser, non-terminals in the grammar are implemented as functions, right? And productions in the grammar become cases within these functions. Productions in the grammar become cases within these functions. Makes sense? The parse tree corresponds directly to the call tree as the parser executes. Alright, cool. I'm going to write some of this down. Top down parser. Let's move this. Which the parser is structured as a set of potentially mutually recursive functions. Top-down parsers are known as LL parsers, where the first L stands for left to right, and the second L stands for leftmost. Implements non-terminals as functions. And reductions in the grammar. Cases within these functions. So it implements non-terminals as functions. Productions in the grammar are cases within these functions. Not expecting myself to remember this, but I'm going to that's terrible. How do I do source mode? This is probably an old version of Anki. Screw it. Top-down parser implements non-terminals as functions, and the productions in the grammar are cases within these functions. Let's see if I can do this. It's not really going to work. I'm not going to remember this second bit for sure. Top-down parser that implements non-terminals as functions. Top-down parsers are known as LL parsers. Left to right, leftmost means it reads in from left to right and generates or constructs a leftmost derivation of the grammar. Okay. from recognizer to parser. The S expression above is merely a recognizer that tells us whether the input can be interpreted as an S expression. It doesn't produce any representation of the S expression it recognizes. However, we can convert it into a parser that produces such a representation with only modest effort. We modify each of the functions to return a value of the appropriate type. For example, we might have parse S return an object, and parse L can return a linked list object. Each production handled in the parser builds the appropriate object from the result of parsed subexpressions. Each production handled in the parser builds the appropriate object from the result of parsed subexpressions. Object parse S, so return scan ID, which returns just an object. If it's left parentheses, we need to parse L and return the result. And parse L returns linked lists of objects. So the first object is the parse S. The second is a linked list of objects. Oh, okay. So we know that L is, because L is equivalent to S concatenate with L, so L can either be an object concatenated with the rest, so L can either be an object and a list of objects, or it can be empty. So object first equals parse S, the rest equals parse L, and we return the whole thing. That goes back into parse S, and then we return the result from parse S. And eventually, I guess eventually we get down to a single object. Which then gets returned up here, and then we return that. For this example, the abstract syntax tree has been kept deliberately simple. In a parser for a real compiler, we would probably want to build the tree out of many more node types corresponding to different language constructs and including additional information such as the position in the input where the syntax was located. While recursive descent parsing is appealingly simple, it doesn't work for all grammars. And for more complex grammars, predicting the correct production involves some subtleties. The next step is to see how to automate the construction of general LL parsers. Awesome. Cool. So the next step Actually, I'm sort of at a crossroads here because I just noticed that the programming assignment 1 is due by lecture 7. So it never actually said that it was out. So I kind of didn't see it until now. But I had a look at it, and it's essentially just everything we learned in the lexical analysis phase. So we could probably just attempt this next before really diving so deep into syntax analysis. Yeah, I might do that. I might attempt to build this Lexa. What else have we got? Top-down parsing, bottom-up parsing. We also have some Dragon chapters to read after this. I probably won't be showing myself reading those, but I'll probably show myself doing the exercises in the book, which is always fun. So anyway, I'll see you guys in the next video.